In 18th century Europe, inside the laboratories of the continent's greatest chemists, something was going wrong. Metals burned in carefully controlled conditions, and then the ash weighed more than the metal that started the fire. This should have been straightforward. Instead, it shattered a theory that had shaped chemistry for the better part of a century. That theory had a name: phlogiston. The story does not begin with Stahl or any single man. In 1667, a German chemist named Johann Joachim Becher proposed what he called terra pinguis, fatty earth. He argued that all combustible materials contained this hidden substance. More than 30 years later, in 1703, the chemist Georg Ernst Stahl refined the concept and renamed it. Phlogiston came from ancient Greek, meaning burning up. It sounded scientific. It sounded inevitable. The logic was almost beautiful. Stahl argued that everything combustible contained phlogiston, a substance released when materials burned. Metals were composed of calx, the inert residue, plus phlogiston. Heat a metal and the phlogiston escaped, leaving only calx. Heat calx with charcoal, which was rich in phlogiston, and you could rebuild the original metal. The theory explained combustion. It explained metalwork. It explained transformation. For 80 years, this framework dominated European chemistry. Chemists built their careers on it. Universities taught it. Researchers designed experiments within it. Then the experiments began to contradict it. The contradiction was simple and undeniable. When a chemist placed a metal in a flame and heated it, the product weighed more than the original metal, not less, more. The phlogiston theory predicted the opposite. If phlogiston escaped during burning, the remainder should weigh less. But the scales showed more weight, not less. Chemist after chemist confirmed the result. The pattern held across all metals. This was not a marginal discrepancy. This was the theory collapsing in real time. In normal science, when experiments contradict a hypothesis, the hypothesis dies and researchers move on. But phlogiston did not die. Instead, the chemists defending it did something remarkable. They modified the theory to fit the evidence in a way that made the theory impossible to refute. Chemists proposed that phlogiston must have negative mass. That claim deserves to sit on the page for a moment. It is so desperate, so obviously constructed to save a failing framework, that it should have been abandoned instantly. Yet it wasn't. If phlogiston has negative mass, then removing it would make the metal heavier. The weight gained would exactly equal the negative mass subtracted. The arithmetic worked. The logic was airtight. And it was completely, impossibly, deliberately wrong. Robert Boyle championed this version. If you accepted negative mass for phlogiston, every contradiction vanished. The theory survived, the framework persisted, and no experiment could ever prove you wrong because any result could be explained by adjusting how much negative mass you invoked. Others took a different path. The French chemist Louis-Bernard Guyton de Morveau proposed a new version. Phlogiston was lighter than air, he argued. This meant that buoyancy from the surrounding air exceeded its weight. Every contradiction vanished. The theory survived through a different, impossible claim. What is striking is not that these defenses eventually failed. It is that intelligent, trained chemists proposed them at all. These were not fools or con artists. They were confronting evidence that directly contradicted the foundation of a theory they had built their careers on. When that happens, the human response is rarely to abandon the framework. It is to modify it, to invent an escape clause, to add a special exception, to allow the old system to survive. For decades, both versions of phlogiston coexisted. Some professors taught negative mass. Others taught that phlogiston was lighter than air. Both groups continued conducting experiments, refining the theory, publishing work that treated phlogiston as real, even as the contradictions mounted. The end came in the 1770s and 1780s, when Antoine Lavoisier conducted experiments of unprecedented precision. He burned metals and gases with meticulous care, measuring mass before and after, accounting for every particle. He found that when a metal gained weight during combustion, that weight came from the air surrounding it. Specifically, from a gas the air contained, a gas we now call oxygen. There was no phlogiston escaping. There was a substance entering. The entire framework was inverted. Lavoisier's work was mathematically undeniable. His measurements were exact. By the end of the 18th century, the scientific community abandoned phlogiston. Not because they wanted to. Not because the negative mass version was disproven. It could never be disproven by design. But because they could no longer defend it without rejecting the basic rules of measurement. The phlogiston story survives in textbooks because it reveals something uncomfortable about how science actually works. The smartest people, the most carefully trained people, chose to defend a theory that contradicted their own evidence. They would not admit they were wrong. The resistance lasted 80 years for a simple reason. Changing a theory means admitting you were wrong, not just to yourself, but to everyone who learned from you and built careers on your work. It means telling students that what you taught with confidence was an illusion. It is easier to invent negative mass, easier to modify the theory, easier to wait until the weight of evidence becomes so overwhelming that you have no choice. That is not a flaw in 18th century chemistry. It is a feature of how human beings respond to being wrong about something they have staked their reputation on. And it happens at every level of science, every decade, in every field. The names change, the framework changes, but the pattern persists. We do not abandon our theories because one experiment contradicts them. We modify our theories until modification becomes impossible. And then, reluctantly, we let them go.